Hi all. Today we will be discussing about gas power cycles. So you're all familiar with the term cycle. Now a process is said to be cyclic. That is, it happens from one state point to then it moves to another state point, then again to another state point, and then returns back to the initial state point. Such a process is called a thermodynamic cycle. Now in thermodynamics we see that we convert heat to mechanical work output, right? So we have a certain process wherein cyclic process wherein a working fluid actually transfers the heat and then or absorbs the heat and then expands to give a work output. Such cycle in which the heat is converted to mechanical work output is termed as power cycles. Now power cycles are actually classified into vapor power cycles and gas power cycles. Vapor power cycles uses steam as working fluid and gas power cycle uses gas as working fluid. This gas can actually be produced by the combustion of a particular fuel and air. In gas power cycles, the supply of heat is by means of combustion of a suitable mixture of air and fuel within a confined space. Now, this confined space may be a combustion chamber or it may be an IC engine. Okay, so so that is the explanation of the term gas power cycle. So basically we will be studying about gas power cycles. Now another term is air standard cycle. Air standard cycles are those cycles which work with certain assumptions known as air standard assumptions. So basic air standard assumptions are: first one, the gas in the cylinder is considered to be a perfect gas, that is, it obeys gas laws. Second assumption is that there is no chemical reaction or thermal dissociation taking place inside the cylinder. Now the third assumption is that the cycle is considered to be a closed cycle. That is, the whatever fluid is inside, it is circulated. It is considered to be a closed cycle. There is no transfer of mass across the boundary. Now next assumption is the physical constants of the gas like Cp, Cv, gamma, etc. does not change. Then the compression and expansion process are assumed to be adiabatic and they take place without any internal friction. That is, they are frictionless or reversible adiabatic process, which is also known as isentropic process. Now since the cycle is considered to be closed, there is only heat transfer across the boundaries of the system. The heat is considered to be supplied from a higher temperature source and the heat is considered to be rejected to a lower temperature sink. Now, these are the assumptions based on which an air standard cycle works, and these assumptions are known as air standard assumptions. Next term is air standard efficiency. Now, air standard efficiency is a term which is used for comparison of efficiency of different cycles, because each cycles will be working based on different fuels and each fuel will be having different calorific value. So we need to neglect the calorific value of fuel in order to compare different cycles. In order to achieve this, we consider air as the working fluid. So air standard efficiency is defined as the efficiency of an engine which is using air as a working medium. This is required in order to compare the efficiency of different cycles. So before moving on to practical air standard cycles, we will see Carnot cycle. You are all familiar with Carnot cycle and you have seen Carnot cycle in your previous classes. So Carnot cycle, as you know, is the cycle which will give you the maximum efficiency that is possible. It gives you the maximum efficiency possible. So Carnot cycle was developed by Nicholas Carnot in 1824 and it is the most efficient heat engine cycle. This cycle consists of two reversible isothermal expansion process. 1 to 2 is one reversible isothermal expansion, and here we have 3 to 4, which is another reversible isothermal process, which is a compression process, isothermal compression process. So it has two isothermal process, and then it has two adiabatic process. 2 to 3 is a reversible adiabatic expansion process, and 4 to 1 is a reversible adiabatic compression process. So basically Carnot cycle has two isothermal process and two adiabatic process. Okay, process 1 to 2 is isothermal expansion process where the temperature remains constant. There is a temperature of 1 to 2 same, only one temperature is there, that is T1, and during this process heat is added into the system. Q in is the amount of heat that is added. So in this coming to PV diagram over here, here yeah, the process marked as A to B. So process A to B is reversible isothermal expansion process where heat Q1 is added at a temperature T1. The temperature during this process is same because it is isothermal process. Then B to C is the here the process 2 to 3, which is reversible adiabatic expansion process. Then C to D is here process 3 to 4, which is again isothermal compression where temperature remains same. So here the temperature at point C and D is same, and this temperature is marked as T2 over here. Here also we can consider the temperature as T2 because here temperature does not change. Here the temperature is T1 itself. So here we can consider temperature as T2. Okay. So here heat is rejected, and then process 4 to 1. 4 to 1 here it is marked as A to D, which is a reversible adiabatic compression process. The same has been represented on TH diagram over here. A to B. A to B is reversible isothermal process, so it is a straight line on TH diagram. Then B, where heat is added at temperature T1. So the heat added is given as Q1, amount of heat added Q1, or here it is Q in, which is equal to T1 into SB minus SA, which is the entropy difference between point B and point A, because Q is equal to TdS. Now B to C is a reversible adiabatic expansion process. Reversible adiabatic is also known as isentropic process, therefore it is a vertical line on the TS diagram. C to D is reversible isothermal compression process. Since it is isothermal process, the temperature remains same, and hence it is a horizontal line on TS diagram. Temperature at C is equal to temperature at D, and the temperature is marked as T2 over here. So T1 is the temperature here and T2 is the temperature here. Here again heat is rejected. Rejected amount of heat Q2 is equal to T2 into SB minus SA. T2 is the temperature at which heat is rejected. SB and SA are the entropies at point C and point D. Since entropy at C is equal to B and D is equal to A, therefore it is T2 into SB minus SA. So heat is rejected. So let us see how we derive the expression for efficiency of Carnot cycle. So efficiency of any cycle is the ratio of work output to heat supplied, because some amount of heat is absorbed from a high temperature source. From that a small amount of heat is rejected to the sink, and the difference is actually converted to work output. So the output by input is the efficiency, and W can be written as QH minus QC. QH is the amount of heat that is received from the higher temperature source, and QC is the amount of heat that is rejected to lower temperature sink. So QH minus QC by QH, which is equal to 1 minus QC by QH. Now here we have to make an expression for the amount of heat that is absorbed from the higher temperature source, that is QH. Okay, so the amount of heat that is absorbed is equal to work done, because it is an isothermal process, and according to first law of thermodynamics we know that delta Q is equal to delta U plus delta W. Now delta U is actually 0, therefore delta Q is equal to delta W. Now work done is equal to integral PdV, that is also known. So integral 1 to 2 PdV is the work done, which can be written as M or nRT ln V2 by V1. Okay, integration has been done, and instead of PV, RT has been substituted, because PV equal to MRT, it is an ideal gas. So nRT ln V2 by V1, that is the expression for heat that is absorbed from a high temperature source. QC is the amount of heat that is rejected to the low temperature sink. Since it is also an isothermal process, Q is equal to W, it is equal to work transfer, because internal energy is 0. And again the equation for work done is integral PdV. So integral PdV on integration, you'll get a PV into ln V2 by V1. Now P into ln V2 by V1. So it is actually RT into ln V3 by V4. I mean V2 by, it is not V2 by V1, V4 by V3. So it is negative sign also considered. We will get RT ln V3 by V4. So now we have expression for heat that is absorbed from the high temperature source and heat that is rejected to the lower temperature sink. Now considering the adiabatic expansion process, here we have an adiabatic expansion happening from point 2 to 3. Now the temperature at 1 2 process 1 2 or at 2 is actually TH. Here it is marked as TH, and at point 3 the temperature is temperature. is actually the lower temperature, that is Tc over here. You can see Tc marked over here. Okay, the temperature is Tc 3 to 4. So actually we have a higher temperature Th from which the heat is applied, and we have a lower temperature Tc at which the heat is rejected. Now for this adiabatic process 2 to 3, the temperature at point 2 is Th and volume is V2. So Th into V2 raised to gamma minus 1 is equal to, at point 3, temperature is Tc and volume is V3. So Tc into V3 raised to gamma minus 1. Okay. Similarly, we'll be considering the next adiabatic process, that is process 4 to 1. In 4 to 1 also, at condition 1, temperature is Th, because 1 to 2 temperature is same. So Th into V1 raised to gamma minus 1 is equal to, at point 4, the temperature here is Tc. Okay, so Tc into V4 raised to gamma minus 1. So rearranging this, we have V2 raised to gamma minus 1 by V1 raised to gamma minus 1 is equal to V3 raised to gamma minus 1 to V4 raised to gamma minus 1, since Th and Tc will cancel out. And from this we have an output, that is V2 by V1 is equal to V3 by V4. Substituting this here, we have QH and QC. So QC by QH is equal to TCln V3 by V4 by THln V2 by V1. Now V2 by V1 and V3 by V4 are same, therefore this will cancel out, and we'll get efficiency is equal to 1 minus Tc by Th. Efficiency is equal to 1 minus Tc by Th. Now what is Tc and what is Th? Tc is the lowest temperature of the cycle and Th is the highest temperature of the cycle. So efficiency of a Carnot cycle is given by 1 minus lowest temperature of the cycle by highest temperature of the cycle. Now next is Stirling cycle. Stirling cycle was invented by Robert Stirling in 1826. Now the execution of this cycle actually requires most innovative hardware, and that is the main reason why it is not commonly used in practice. Stirling cycle consists of two isothermal process. Here you can see two isothermal process and two constant volume process. Now what happens here is actually the PV diagram is PV diagram and TS diagram are shown here. In the PV diagram, state point 1 to 2 is an isothermal expansion process. 2 to 3 is a constant volume heat rejection process where the heat is transferred to a regenerator. That is, the internal heat of the working fluid is transferred to a regenerator in this process 2 to 3. 3 to 4 is again a reversible isothermal compression process where the heat is rejected. And 4 to 1 is again a constant volume heat transfer process where the internal heat from the regenerator is given to the working fluid. So here the internal heat from the regenerator is given back to the working fluid. Okay. So process 1 to 2 is isothermal expansion process where an amount of heat QS is applied externally. In 2 to 3, a part of the working fluid supplies its heat to regenerator. 3 to 4, an amount of heat is rejected externally to the sink. 4 to 1, where the regenerator gives back the heat to the working fluid. So these are the basic process that is happening in a Stirling cycle. So here the regenerator is assumed to be a reversible heat transfer device. The regenerator can be a wire or a ceramic mesh or any kind of porous plug with a high thermal mass capacity. So during this regeneration process, the heat is transferred to the regenerator during first half, and then heat is transferred back to the working fluid in the remaining half of the cycle. So let us see how we can derive an expression for efficiency of the Stirling cycle. Now this Stirling cycle is again shown on temperature entropy diagram also. So isothermal process is shown as a straight line because temperature remains same, and then constant volume process is represented here. Now the heat supplied QS, heat supplied during the isothermal process 1 to 2. During process 1 to 2, heat supplied is P1 V1 ln V2 by V1. And now V2 by V1, actually we have a ratio known as compression ratio. Compression ratio is the ratio of total volume to clearance volume. Total volume, that is if we consider a piston cylinder arrangement over here, okay, we are considering a piston cylinder arrangement over this space. Now this is the cylinder head, this line is the cylinder head. We have a piston over here which is reciprocating or moving back in this direction, and it will move until this end. So this is the total volume. V3 or V2 is the total volume, and piston moves inwards until this point. This is the inner dead center. Let us consider this as inner dead center. That means up to this point piston moves. Now the remaining volume is clearance volume. So V4 or V1 is the clearance volume, and V3 or V2 is the total volume. Now total volume by clearance volume is known as compression ratio. So here total volume is V2 or V3. Okay, V2 or V3 represents the total volume, and V1 or V4 represents the clearance volume. So here we have a ratio V2 by V1. Now V2 by V1 represents compression ratio R. Compression ratio R. Here it is this is a mistake over here. It is actually V2 by V1. In top it has to be V2 and bottom it is V1. That is total volume by clearance volume. This is true. V2 by V1 is actually compression ratio R. So P1 E1 ln R. Heat supplied instead of P1 E1 MR T1 ln R. Okay, so this is the expression for heat supplied. Now for Stirling cycle, the compression ratio is total volume by clearance volume. Total volume is V2 by V1. This is V2 by V1. This is compression ratio R. This is true. Don't look into this. This is actually wrong. This is V2 by V1. This is a printing mistake over here. Now heat rejected QR. Heat rejected during the isothermal compression process. Heat rejection is happening from in process 3 to 4. It is isothermal compression process where heat is rejected. It is P3 V3 ln V3 by V4. Now V3 by V4 is actually V2 by V1 since volume is same. So it is again P3 V3 ln R or MR T3 ln R. So this is the amount of heat that is rejected during the process. Now net work done. Work done is the difference between heat supplied and heat rejected. So MR ln R is a compression ratio into TH minus TL. We can TH and MR ln R is a common term here and common term here. So it is MR ln R into T3 is actually T3 minus T1 minus T3. So instead of that here instead of T1 we have written as TH, that is the highest temperature at which heat is applied, and instead of T3 we have written TL, that is the lowest temperature at which heat is rejected. So the difference between TH and TL, MR TL and R into TH minus TL. So here process 2 to 3 and process 4 to 1 are constant volume process. So for a constant volume process work done is 0. Therefore thermal efficiency is equal to output by input, that is work output by heat supplied. Work output is the difference between heat supplied and heat rejected, that is MR ln R into TH minus TL by heat supplied is MR ln R into TH. It is TH minus TL by TH or 1 minus TL by TH or 1 minus T2 by T and 1 minus TL by TH. So this is the expression for efficiency of Stirling cycle. Now if you go back and see the expression for efficiency of Carnot cycle, it is also same, 1 minus Tc by Th, that is the lowest temperature of the cycle by highest temperature of the cycle. So this efficiency of Stirling cycle is actually equal to that of Carnot cycle when both are working within the same temperature limits. Okay, when both Carnot cycle and Stirling cycle are working within the same temperature limits, their efficiencies are also same. But it's not possible to achieve 100% efficiency in a regenerator, because in Stirling cycle we are using a regenerator. We have already discussed about that. Because in both constant volume processes, during one half the heat of the fluid is given to the regenerator, and during the second half the regenerator gives back the heat to the fluid. Now it is impossible to have 100% efficiency for the regenerator, and hence the efficiency of Stirling cycle will be always less than the efficiency of Carnot cycle. So this will lead to this inefficiency of the regenerator will lead to a reduction in efficiency of the Stirling cycle. That is a practical situation. But if you consider this theoretically, or if you consider 100% efficiency for the regenerator, then if both Carnot and Stirling cycle are working between the same temperature limits, then both will have the same efficiency. But in real case it will be different because the regenerator will not have 100% efficiency. Now next is Ericsson cycle. Ericsson cycle was invented by John Ericsson in 1850. Ericsson engine actually works on principle of Ericsson cycle, which comprises of regenerator and heat exchanger. Now this actually Ericsson cycle consists of two isothermal process and two constant pressure process. Here you can see 4 to 1 is a constant pressure process and 2 to 3 is also a constant pressure process. Then we have two isothermal process, 1 to 2 and 3 to 4. During isothermal process 1 to 2 heat is applied Q in, and 3 to 4 heat is rejected Q out. The same has been shown on temperature entropy diagram. 1 to 2 is the isothermal process in which heat is supplied from a high temperature source, Q in so equal to Qs, and 2 to 3 is a constant pressure process. Now, during the constant pressure process, internal heat is transferred from working fluid to regenerator. During this constant pressure process, the internal heat of the working fluid is transferred to regenerator. 3 to 4 is an isothermal heat rejection process where heat is rejected, Q out equal to Qr is rejected to sink. 4 to 1 is constant pressure process where again the internal heat is transferred from the regenerator back to the working fluid. So during 4 to 1, during process 4 to 1, the internal heat is transferred back to the working fluid. It is same as Stirling cycle. The only difference is that the heat transfer happens at constant pressure. Internal heat transfer from the working fluid to the regenerator and from regenerator to the working fluid both happens at constant pressure over here. Okay. So to see the derivation for efficiency of Ericsson cycle, heat supplied QS during process 1 to 2, that is isothermal process. It is equal to work done because change in internal energy is 0 as temperature remains same. So it is given by P1 V1 ln P1 by P2 instead of V2 by V1 can be written as P1 by P2, which is equal to RT H. TH is the highest temperature from which heat is applied into ln P1 by P2. Okay. Now heat Q2 to 3, that is heat rejected during the process 2 to 3. This is heat supplied Q1 to 2 and heat rejected Q2 to 3 is equal to Cp into TL minus Th. Okay, let this be here. We will consider this later. Now heat rejection Qr. Okay, here we have found out an expression for heat that is supplied from the high temperature source. It is equal to P1 U1 ln P1 by P2 or RTH ln P1 by P2. Now heat rejected Qr during the process 3 to 4. So during process 3 to 4 heat is rejected, which is equal to W3 to 4, which is equal to P3 V3 ln P4 by P3. That can again be written as RT ln. TL is the lowest temperature at which the heat is rejected to the sink ln P4 by P3. Now P4 is actually equal to P1. P4 is actually equal to P1 and P3 is actually equal to P2. So this can be written as P1 by P2. So RTL ln P1 by P2. Now for an ideal regeneration process, the heat that is supplied to the Q2 to 3, Q2 to 3 is the heat that is supplied to by the fluid to the regenerator. CPL and CP into TL minus, because heat is applied constant pressure into TL minus TH, and Q4 to 1 is the amount of heat that is rejected by the regenerator to the working fluid, that is again at constant pressure. So Cp into Th minus TL, that is same. Therefore thermal efficiency of the cycle is given by efficiency equal to work output by input. Work output is actually the difference between the heat supplied and heat rejected, that is R ln into P1 by P2 into Th minus TL by heat supplied. So the common terms are cancelled and we'll get Th minus TL by Th or 1 minus TL by Th. That is 1 minus lowest temperature by highest temperature. So this efficiency is also same as Stirling cycle efficiency. That means both Stirling and Ericsson cycle have same efficiencies as that of Carnot cycle when they are working between the same temperature limits. But in practical case, the regenerator has a efficiency less than 100%. Therefore, the efficiencies of Stirling and Ericsson cycle will be less compared to Carnot cycle in practical situation. But if you look theoretically, both Stirling and Ericsson cycle have same efficiency as that of Carnot cycle if they are working between same temperature limits. Moving on to Otto cycle. Now Otto cycle, also known as constant volume cycle, the petrol engines actually work on this cycle. The cycle was introduced by scientist Otto in 1876. Let us see the cycle. So cycle has been represented here. The cycle has a reversible isothermal compression process 1 to 2, a constant volume heat rejection process 2 to 3, a reversible isothermal expansion process 3 to 4, and a constant volume heat rejection process 4 to 1. Heat is supplied during constant volume process 2 to 3 and heat is rejected during constant volume process 4 to 1. The same has been represented on TS diagram. 1 to 2 is reversible adiabatic compression. Reversible adiabatic is also an isentropic process, therefore it's a vertical line on TS diagram. 2 to 3 is a constant volume heat addition process, Q1 amount of heat is added. 3 to 4 is a reversible adiabatic expansion process. Since reversible adiabatic is also isentropic, it is a vertical line on TS diagram. and 4 to 1 is constant volume heat rejection process, where Q2 amount of heat is rejected out. Now we have to derive an expression for efficiency of the cycle. So heat is added during constant volume process. Heat added during constant volume process given as mCv T3 minus T2. mCv T3 minus T2, because during adiabatic process no heat is added. Heat transfer is zero, reversible adiabatic process. So heat added during constant volume process mCv T3 minus T2. Similarly, heat is rejected at constant volume process, that is 4 to 1. So mCv T4 minus T1 is the amount of heat that is rejected during constant volume process Cv, and heat is rejected from 4 to 1. So T4 minus T1. During the two reversible adiabatic or isothermal process, sorry, isentropic process, two reversible adiabatic process are here. This is one reversible adiabatic process 1 to 2, and 3 to 4 is another reversible. I think earlier I have explained this as isothermal. I'm sorry. This is reversible adiabatic process 1 to 2 is also reversible adiabatic, and 3 to 4 is also reversible adiabatic. So it is isentropic over here. So during reversible adiabatic process, heat transfer is 0. Therefore, the net work done is actually heat supplied minus heat rejected. That is, and efficiency is equal to output by input, work output by heat supplied. Work output is the difference between heat supplied and heat rejected by heat supplied, or 1 minus QR by QS. 1 minus QR is mCv T4 minus T1. Here we have written mCv T4 minus T1, and QS is mCv T3 minus T2. So common terms are cancelled, and we have 1 minus T4 minus T1 by T3 minus T2. Now coming to a ratio known as compression ratio, we have already seen this ratio. Compression ratio R is defined as the total volume, as a ratio of total volume to clearance volume. It is a ratio of total volume to clearance volume, or volume before compression by volume at the end of compression. Volume before compression is V1, which is equal to V4, and volume after compression is V2, which is equal to V3. So it can be written as V1 by V2 is equal to V4 by V3. Now for an isentropic process, we can write temperature volume relationship as for isentropic process 1 to 2, T2 by T1 is equal to V1 by V2 raised to gamma minus 1. V1 by V2 is actually compression ratio R, so it is R raised to gamma minus 1. For isentropic process 3 to 4, we can write the same relation. T3 by T4 is equal to V4 by V3 raised to gamma minus 1. V4 by V3 is also R, so you can written as T3 by T4 is equal to R raised to gamma minus 1. Okay. Now T2 by T1, okay, now T2 by T1 is equal to T3 by T4, which implies that T3 by T2 is equal to, this is a simple rearrangement here, since these two terms represents T2 is equal to T1 into R raised to gamma minus 1, and T3 is equal to T4 into R raised to gamma minus 1. So you can substitute that here. From this equation, we have T2 is equal to T1 into R raised to gamma minus 1. So instead of this T2, you can write it as T1 into R raised to gamma minus 1, and instead of this T3 over here, you can write it as T4 into R raised to gamma minus 1. Okay, T3 is T4 into R raised to gamma minus 1, and T2 is T1 into R raised to gamma minus 1. So you take R raised to gamma minus 1 as common outside. This will be T4 minus T1. You can cancel that out. Then you will get 1 minus 1 by R raised to gamma minus 1. 1 minus 1 by R raised to gamma minus 1. You just have to substitute this here. That is T2 is equal to T1 into R raised to gamma minus 1. You substitute it here. Instead of T2, it is T1 into R raised to gamma minus 1. Then instead of T3, you can write it as T4 into R raised to gamma minus 1. So T4 minus T1 is a common term. When cancelling that, you will get 1 minus 1 by R raised to gamma minus 1. So that is the efficiency of Otto cycle. Efficiency equal to 1 minus 1 by R raised to gamma minus 1. So here, efficiency of Otto cycle depends upon compression ratio R, because gamma is a constant value, and for air it is 1.4. So the efficiency is a function of compression ratio only. So if you increase the compression ratio, you can increase the efficiency of Otto cycle, but again it has a limitation, because once you go on increasing the compression ratio, that will lead to detonation or knocking in petrol engines. Okay, next is diesel cycle. Now diesel cycle is also known as constant pressure cycle. Here you can see the PV and TS diagram of a diesel cycle. We have a reversible adiabatic compression process. a constant pressure heat addition process, a reversible adiabatic expansion process, and constant volume heat rejection process. So you have to remember, in diesel cycle, heat addition is at constant pressure and heat rejection is at constant volume. The same has been represented on TS diagram. 1 to 2 is reversible adiabatic. It is also known as isentropic. That is why it is a vertical straight line on TS diagram. Then 2 to 3 is a constant pressure heat addition process. Given amount of heat is added. 3 to 4 is isentropic reversible adiabatic or isentropic expansion, and 4 to 1 is constant volume heat rejection process. Q2 amount of heat is rejected as constant volume. Here it is constant pressure. Okay, now let us so this diesel cycle is also known as a constant pressure cycle. It has been invented by Dr. Rudolf Diesel in 1897. So diesel cycle, let us see how we derive an expression for efficiency of diesel cycle. So heat supplied, here heat is supplied, since we know that process 1 to 2 and 2 and 3 to 4 are reversible adiabatic, there is no heat transfer during that process. So heat is transferred only during constant volume process 2 to 3, sorry, constant pressure process 2 to 3 and constant volume process 4 to 1. So heat supplied during process 2 to 3 is equal to, it is constant pressure MCP T3 minus T2. Heat rejected during constant volume process 4 to 1 is equal to MCV T4 minus T1. Efficiency is 1 minus heat rejected by heat supplied. So it is 1 minus MCV T4 minus T1 by MCP T3 minus T2. M can be cancelled. Cp by Cv is gamma. So this can be written as 1 by gamma into T4 minus T1 by T3 minus T2. Okay. Now we have seen compression ratio. Compression ratio is the ratio of total volume by clearance volume, or volume before compression by volume after compression. Volume before compression is V1, which is also equal to V4. Volume after compression is V2. So compression ratio R is equal to V1 by V2. Now we have one more ratio defined here known as cutoff ratio. Cutoff ratio is the ratio of V3 by V2, that is volume after constant pressure heat addition V3 by volume before constant pressure heat addition V2. V3 by V2 is known as cutoff ratio, represented as a rho, cutoff ratio rho. Now for process 1 to 2, it is a reversible adiabatic process, so we can write temperature volume relationship. T2 by T1 is equal to V1 by V2 raised to gamma minus 1, or R raised to gamma minus 1, or T2 is equal to T1 into R raised to gamma minus 1. Now for the constant pressure process 2 to 3, since it is a constant pressure process and it is ideal gas, we can write it as P1 V1 by T1 is equal to P2 V2 by T2. Pressure is same, so excluding pressure, T3 by T2 is equal to V3 by V2. Now V3 by V2 is actually cutoff ratio rho, or T3 is equal to rho into T2. T3 is equal to rho into T2. Also we have already written that we know that T2 is equal to T1 into R raised to gamma minus 1. Substituting that here, we get T3 is equal to rho into, instead of T2, T1 into R raised to gamma minus 1. So we have converted T3 in terms of T1. Here we have converted T2 in terms of T1. Now we have to find out T4 also in terms of T1. For that we have process 3 to 4. 3 to 4 is actually reversible adiabatic expansion process. So T3 by T4 is equal to V4 by V3 raised to gamma minus 1. V4 by V3. Now here V4 by V3 is written as V1 by V3 because V4 is equal to V1. We know that V4 is equal to V1. So V1 by V3, which is equal to V1 by V2 into V2 by V3. This can be done because V2 and V2 cancels out. It becomes V1 by V3. Now what is V1 by V2? Actually V1 by V2 is R, right? V1 by V2 is R, and V3 by V2 is rho. So this can be written as R by rho. Okay. So so here V4 by V3 is written as R by rho raised to gamma minus 1. So T4 is equal to T3 by R by rho raised to gamma minus 1. Now what is T3? T3 is actually T1 into R raised to gamma minus 1. So instead of T3, we can write, sorry, rho into T1 into R raised to gamma minus 1. Rho into T1 into R raised to gamma minus 1 by R by rho raised to gamma minus 1. Cancelling out the common term, we will get T1 into rho raised to gamma. So here we got T4 in terms of T1. So we have converted T2, T2, T3 and T4 in terms of T1. Substituting that in this expression of efficiency, instead of T4, T3 and T2, we have expressions in terms of T1. So instead of T4, T1 into rho raised to gamma minus T1 by, instead of gamma into, instead of T3, we have rho into T1 into R raised to gamma minus 1 minus, instead of T2, T1 into R raised to gamma minus 1. Okay. So here we can T1 is common term, we can cancel this T1 and then rearranging we get efficiency of diesel cycle is equal to 1 minus rho raised to gamma minus 1 by gamma into rho raised to gamma minus 1 into rho minus 1, or 1 minus 1 minus 1 by gamma into R raised to gamma minus 1 into rho raised to gamma minus 1 by rho minus 1. This is the expression for efficiency of diesel cycle. Here gamma is index of adiabatic expansion, for air it is 1.4, R is compression ratio and rho is cutoff ratio. Okay, and here rho is greater than 1, rho will be always greater than 1, and the efficiency of diesel cycle is less than that of Otto cycle for the same compression ratio. If compression ratio remains same, then efficiency of diesel cycle is less than efficiency of Otto cycle. But in normal case or practical case, the compression ratio of diesel cycle is more, and hence the diesel cycle will have more Ericsson efficiency of diesel cycle will be more. Okay, next is a term known as mean effective pressure. Mean effective pressure is defined as that constant pressure to which the cylinder is subjected, so that the same work is developed as that of varying pressure. So mean effective pressure is the ratio of work done by swept volume. Mean effective pressure MEP is the ratio of net work done by swept volume. Swept volume is V1 minus V2, because V1 is total volume and V2 is clearance volume. V1 minus V2 is swept volume. So here actually we see for a normal cycle from 1 to 2, 2 to 3, 3 to 4 and 4 to 1. This is this normal cyclic process. This actually represents an Otto cycle. So here the pressure is continuously varying. So instead of this continuously varying pressure, we are assuming a constant mean pressure. Now this line over here, this actually represents a constant mean pressure, such that this mean pressure will give you the same work output as that of this varying pressure. So in actual cycle the pressure is varying. Instead of that, we are considering a constant mean pressure which will give you the same work output as that of the varying pressure. That pressure is known as mean effective pressure, and it is a ratio of work done by swept volume. Now next is dual combustion cycle. So dual combustion cycle has actually two modes of combustion. See in this paper diagram we have process 1 to 2, which is reversible adiabatic compression. 2 to 3 is constant volume heat addition, 3 to 4 is constant pressure heat addition, and 4 to 5 is reversible adiabatic expansion, and 5 to 1 is constant volume heat rejection. So here heat addition happens at two different processes. That is why it is known as a dual combustion cycle. Heat addition partly at constant volume and heat addition partly at constant pressure. That is a dual cycle. So here again, if you want to derive the, so it is seen in TS diagram also. 1 to 2 is reversible adiabatic compression, therefore it is a vertical straight line. 2 to 3 is constant volume heat addition, 3 to 4 is constant pressure heat addition, 4 to 5 is isentropic expansion, and 5 to 1 is constant volume heat rejection. So here the total heat supplied, QS is equal to heat supplied during process 2 to 3, which is constant volume, plus 3 to 4, which is constant pressure. So you can write the expression for both, because for constant volume it is MCV T3 minus T2, and for constant pressure it is MCP T4 minus T3. MCP T4 minus T3. Total heat rejected is heat rejection is happening here at constant volume, that is MCV T5 minus T1. So total work output is heat supplied minus heat rejected, that is written over here, and efficiency equal to output by input, that is output is a total work output by input is total heat supplied. So this is the now you can cancel out the common terms, and then I will get dual cycle efficiency is equal to 1 minus T5 minus T1 by T3 minus T2 plus gamma into T4 minus T3. So this is the expression for efficiency of dual cycle in terms of temperature. Again you can go for some rearrangements. I am not explaining the rearrangements. It is simple, you can read it out, because compression ratio or you already know. Then pressure ratio, now this is a new ratio that is defined here, pressure ratio or explosion ratio beta, that is a ratio of P3 by P2, because here we have an additional term. Usually we don't have this point, so we have an additional term P3 by P2, that is the pressure after constant volume heat addition by pressure before constant volume heat addition, that is the pressure ratio beta or explosion ratio. Then cutoff ratio, we have defined cutoff ratio. Now substituting these ratios over here and converting all the temperatures, that is T5, T3, T2 and T4 in terms of T1. So here we are converting all this in terms of T1. This is simple. You can just read it out in terms of T1 and substituting in the expression for efficiency. We will get efficiency of dual cycle as 1 minus 1 by r raised to gamma minus 1 into beta into rho raised to gamma minus 1 by beta minus 1 plus beta gamma into rho minus 1. Here only the additional term is beta. Okay. Rest of the terms, R is compression ratio, gamma is index of adiabatic expansion, that for air is 1.4. Then rho is cutoff ratio, and beta is the only additional term that we have defined here, that is the explosion ratio. Okay. So finally we have now studied about all different gas power cycles, and now we'll compare the Otto cycle, diesel cycle, and dual combustion cycle. So usually the efficiency of all cycles depends on compression ratio. So here efficiency and compression ratio has been plotted, compression ratio on x-axis and efficiency of y-axis. Now we can see that it is clear from this figure that Otto cycle is more efficient as compared to dual and diesel cycle. But as you go on increasing the compression ratio, after some point the efficiency of Otto cycle will tend to be straight and then it will decrease because of the because as you go on increasing the compression ratio, the unnatural combustion or abnormal combustion happens, that is known as knocking, due to which efficiency of this Otto cycle will tend to decrease after this. But for diesel cycle and dual fuel cycle, the efficiency will go on increasing as you increase the compression ratio. But for a particular, if you take a particular range of compression ratio, the Otto cycle is more efficient compared to dual and diesel cycle. Now comparison of Otto, dual and diesel cycle for constant compression ratio and heat supply. That is, compression ratio is constant. All cycles are having same compression ratio and same heat supply. Now let us see the PV and TS diagram for the same. So in this PV diagram, 1, 2, 3, 4, that represents diesel cycle, because 1 to 2 is reversible adiabatic compression, 2 to 3 is constant pressure heat addition, 3 to 4 reversible adiabatic expansion, 4 to 1 is constant volume heat rejection. So 1, 2, 3, 4 is diesel cycle. Then 1, 2, 3 double dash, 1, 2, 3 double dash and 4 double dash, that is Otto cycle. And 1, 2, 2 dash, 3 dash, 4 dash is dual cycle. So here heat supply is same. Okay, for all these three cycles heat supply is same. So we can go to TS diagram, because only in TS diagram we can know about heat transfer. In TS diagram, 1, 2, 3, 4, again 1, this is diesel cycle. So 2 to 3 is the heat added over here. Then 1, 2, 3 double dash, 4 double dash. So this is 2 to 3 dash is heat added in Otto, 3 double dash is heat added in Otto cycle. Then 1, 2, 2 dash, 3 dash, 4 dash, 1 is dual cycle. Heat addition is 2, 2 dash to 2 dash, 3 dash. Now heat added is same. For all the cycles heat added is same. That means efficiency will depend on heat rejected. Now efficiency is 1 minus heat rejected by heat supplied. So heat rejection is less for Otto cycle. See here, for Otto cycle heat rejected is 4 dash to 1 only. Area under 4 dash, 4 double dash to 1 is heat rejected for Otto cycle. Now for diesel it is area under 4 to 1, which is more, and for dual cycle in between, that is 4 dash to 1. So the heat rejected is less for Otto cycle, and hence Otto cycle will be more efficient compared to dual and diesel cycle. So Otto cycle, for same compression ratio and heat supply, Otto cycle is more efficient compared to dual and diesel cycle. Now comparison of Otto and diesel cycle, here dual cycle is not drawn. Otto and diesel cycle for maximum pressure and heat supply. So maximum pressure and heat supply is same. Let us see in PV diagram, 1, 2 dash, 3 dash, 4 dash, 1. This is Otto cycle, and diesel cycle is 1, 2, 3, 4. So here again you can see that the maximum pressure is same, because here again 3 dash and 2, maximum pressure is same here, and heat supply is also same. So here in TS diagram, 1, 2, 1, 2, 3 dash, 4 dash, 1, and 1 2 3 4. 1 2 3 4, this is the diesel cycle. 1 2 3 4 is diesel cycle, and 1 2 3 dash 4 dash is petrol cycle or Otto cycle. So here heat supplied is same, so heat rejection is more for Otto cycle, because for Otto cycle heat rejection is from 4 dash to 1, and for diesel cycle heat rejection is from 4 to 1. So heat rejection is less for diesel cycle, and hence diesel cycle is more efficient than Otto cycle. So for the same maximum pressure and heat supplied, diesel cycle is more efficient than Otto cycle. Now in the next case, last case, is comparison of Otto and diesel cycle for maximum pressure and heat rejected. Maximum pressure and heat rejected remain same. So in PV diagram, 1 2 3 4, this is Otto cycle. 1 2 double dash 3 4 1, this is diesel cycle, and 1 2 dash 3 dash 3 4 1 is dual cycle. So yeah, the maximum pressure is same for all cycle, because maximum pressure is 2 dash 3 dash and 3, which is same for all cycles. Now coming to temperature entropy diagram. So here 1 1 2 3 4, that is Otto cycle. So Otto cycle, again heat rejection is same. See here, heat rejection is same, but heat supplied is from 2 to 3. 2 to 3 is heat supplied. Now for the case of Otto cycle, 1 2 double dash 3, sorry, for the case of diesel cycle, because for the case of diesel cycle it is 1 Otto cycle here we have seen. Now diesel cycle, 1 2 double dash 3 4 1, 1 2 double dash. So let us see here, 1 2 double dash to 3. So this is your diesel cycle. Heat supplied is from 2 double dash to 3. 2 double dash to 3 is heat supplied for diesel cycle. It is written over here. 2 double dash 3 is heat supplied for diesel cycle. 2 to 3 is heat supplied for Otto cycle, and for dual cycle it is from 2 dash to 3 dash and 3 dash to 3. This is heat supplied. So heat supplied is less for Otto cycle, and it is maximum for diesel cycle. Since heat supply is more for diesel cycle, the diesel cycle will have higher efficiency. So for the case of maximum pressure and heat rejection, diesel cycle will have higher efficiency compared to dual and Otto cycle. So this is the comparison between Otto, diesel and dual fuel cycle for different cases. Thank you, and wishing you all a happy learning.